The main flavors of image processing today. So without further ado, I'd like to introduce Dr. Joachim Frank.
Okay, thanks a lot. I don't know how far the video range goes here. Yeah, I'm fine. Okay. So I wanted to talk about single particle reconstruction and essentially go into a lot of conceptual details that were in fact part of the initial development of programs. And these are concepts that are very useful, and maybe sometimes you don't come across them because you're working with entire packages, which I would call black boxes. So imaging in the transmission electron microscope means that electrons go all the way through the object as opposed to being scattered off it, and then we observe a two-dimensional projection. And the transmission means that the signal is generated from electrons passing through the specimen. And the two-dimensional projection is a line integral over the 3D density along the beam. You can think about integrals going all the way through and summing up over the object that they encounter. Okay. So then we have a projection theorem that tells us on how to get from two-dimensional to three-dimensional. I'm going to get into this a little later. The pioneers in the field of three-dimensional reconstruction in electron microscopy, and in fact in three-dimensional reconstruction in general, were Aaron Klug and David Durcier. It's not been done in any other field. It goes back to algorithms that or mathematics that were developed in 1907 by a fellow who was called Radon. The first 3D reconstruction, Aaron Klug. What happened?
That's an interesting question.
Carl walked out and the whole thing broke down. Okay. I think we need Carl simply to be here.
See, he can never leave, and then everything will be fine.
Yeah. Okay. Okay, so Aaron Klug, David Durcier, and they performed a three-dimensional reconstruction on the bacteria phage tail. It was a relatively easy structure because it's helical and the single view was already sufficient. So now, from that we know that we need multiple projections in order to get a 3D structure. And here are different data collection strategies for 3D reconstruction. This here you will recognize as a CAT scan. There is a patient who is stationary, and an X-ray source and detector are turned around in equal increments all the way around, and that's how the projections are collected, and then a single 3D reconstruction is produced, and that shows then the patient's interior in detail. Electron tomography is exactly equivalent, except that the molecule is now rotated in steps, and the electron beam detector arrangement is stationary. And then we have a radically different way of looking at this. We have the beam detector stationary in the microscope, and the molecule essentially rotates around all by itself. We have many copies of the molecule, and they are in random orientations. So if we are clever enough to determine the orientation of all these molecules a posteriori, namely from the projections, then we can essentially bypass this entire requirement of tilting. So I'm going to talk about this particular data connection geometry. What happens now? Okay. So now, why would we do single particle data collection, and why not tomography? So the reason is radiation damage. So if we have any kind of energy, for instance electrons, and they hit an atom, then there are two different ways of interaction, and one of them is inelastic and the other one elastic. So elastic scattering, no energy is transferred, no radiation damage, and these electrons are useful for image formation. So it's elastic scattering. Elastic means no dissipation of energy. Inelastic scattering leads to ionization, that's indicated here. An electron is knocked out, which produces a charge for the entire atom. It's associated with bond breaking and the formation of radicals. Radicals are bad. Why do we need low temperature? The cryo, they are double purpose. One is to present the molecules in a close to native environment in high vacuum to the beam. It's obviously a challenge to have vacuum and have something aqueous in the system. And in order to get the very low gas pressure, low pressure for water vapor, it's useful to have very low temperatures. Now the second one, maybe that's not so widely known, is to trap the damaged molecules and keep the radicals from migrating, which would cause further damage. So in fact, we might have damage there, but we don't see it because the radicals have no chance to migrate. Okay, so that's important to keep in mind. There's double purpose in going to these low temperatures. So now, here we have scattering geometry. There's a thin sample. It needs to be thin because otherwise we get multiple scattering and there's almost nothing left here, down here. So we have scattered electrons. Here's the direct beam, and the electrons that are scattered over a low angle produce low resolution. The ones over high angle, high resolution. So we can essentially, for giving scattering geometry, we can already put a reciprocal scale here. Here's the high resolution, here's the low resolution. Now the image formation, this diagram here is up here. Now the lens intercepts these rays, and the lens is supposed to reconverge all the beams that come from a single point into a single point again. Now you can see with any instrument like the electron microscope, this is not going to be ideal. We don't get a single point back because of wave aberrations. So instead of a single point, we get an extended point. So we could choose different different planes here, and we will see that for certain planes we get sort of a minimum of confusion, but still we have a finite width of the image of a single point. We're going to come back to what it means to have an image of a single point. Okay, we've been talking about radiation damage. The damage affects the small features first, and then the larger features. So if we have a molecule, we keep irradiating it, then we get sort of the deterioration of secondary structure and so forth, and then it gets worse and worse, and we get a more and more blurred image of the molecules. So we can define a critical exposure as the exposure to get to a certain point in the radiation damage, and so that is a function of spatial frequency. Now, all these measurements of the radiation damage were first done with crystals, and here we see the curve for crystals, which indicates that crystals that the radiation damage affects crystal much more. than the molecules themselves. Now, what could be the reason? Well, obviously, the reflections are sensitive to any disorder. So it could be that the molecules get disordered at the same time as the damage occurs, and the disorder is also reflected in the size of these amplitudes. So I'm going to go a little bit in specimen preparation. First of all, we want to have a purified sample, but then recently the standards of purity have changed because of the advent of classification. So we can think about classification as a computational purification. We actually see a great advantage to be able to see the molecule in all its different forms in binding states. Okay, and previously, without the classification, we aim to get one particular structure with one particular ligand binding state, for obvious reason. So then the sample is applied to the EM grid. It's a thin film, and so this is sort of a pretty good target value and suspended over holes. Since the value has not come up yet here, the maximum thickness for electrons with 300 kV is something like 1/4 of a micron, which is 2,500 angstroms. Anything above that causes just too much multiple scattering, and the signal gets weaker and weaker. Okay. But we normally, with the molecules that we want to look at, we normally we can live with 1,000 angstroms, and that's sort of pretty much a target value. For size comparison, the ribosome is 250 angstroms. So then carefully controlled blotting is a critical step, because we want to aim, with the blotting, we want to aim at getting this kind of thickness. So we want to have control over the blotting force and the blotting time. And obviously that's very difficult to do if we use a manual blotting. So the coverage with molecules is determined obviously by sample concentration, by the geometry and makeup of the metal grid. Copper, molybdenum, gold has been used. Copper has been traditional. Molybdenum was used for some time, or proposed, because the heat expansion is matched to carbon. And then gold, I'm going to have a couple of slides about this, has now been used to avoid charge-induced vibrations, and that has been a very major advancement. I'm sort of missing something here, but all right, I'm going to go on. So the plunge freezer, this is the idea. We have a grid at the end of tweezers, and a droplet with the molecules is put on the EM grid, and then blotting is applied to get a thin aqueous layer, and then this entire arrangement is dropped down to the temperature of liquid nitrogen. But we need to drop it into something else but liquid nitrogen. If we dropped it in liquid nitrogen, then we would get bubbles that form. We would get air bubbles, and the air bubbles prevent very rapid exchange of heat. And that's why we drop into liquid ethane that is held on liquid nitrogen temperature. Now this whole idea here is to keep the molecules suspended in in a liquid that retains the structure of a liquid, and this is called vitreous ice. So if this process of immersion and heat exchange is too slow, then we get the formation of crystalline ice, and they crush the molecules, they affect the structure. So this is a hand-built device, $200. This is more in the range of $70,000, which is doing the same thing, except this is the Gatan version, and there's another version by FEI. So the idea is that to have a controlled environment here, because otherwise here the outcome is going to be dependent on the weather and on the temperature and so forth. Here, this is all controlled, and then the blotting force is controlled and so forth. The specimen supports, so I already talked about the EM grid of copper. All the grids are 3 millimeter, and so now there is a support of carbon, and the carbon itself has holes. And these used to be homemade by some kind of a recipe, very complicated recipe. But then meanwhile, we have these quantifoils, which have holes of an exact size and in an exact arrangement. And obviously, these make data collection and automation of data collection much more easy. And they also allow control of the geometry, which determines the meniscus, the formation of the meniscus at the edge. So there is something else, C-flat grids. I don't know, maybe they were they came out of Scripps or somewhere else, but they have different kind of edges, different thickness, different geometry, and they're all that's all important for the control of the meniscus at the edge. So here is sort of you see a data collection with Legenon, where you see that the cursor hones on all these different holes, and then in these automated data collection systems have a way of determining whether a hole is good or not, and they use the average density and the average and the standard deviation in a 2D diagram to determine whether this is could be useful or not. So these are sort of the different hierarchies. Here's the EM grid. There's a single grid square, which then is covered with quantifoil. Then we have a single hole in the carbon film, and we could have another thin layer of carbon on top, or we could just have a freely suspended water. And then we have the protein or ribosomes or RNP embedded here. So this is an actual micrograph, and it shows you the meniscus effect. Here's the border of the hole, and here's an image field, and so anything that is closer to the hole is all of a sudden crowded with molecules. And here, going away from the hole and toward the center, the surfaces are too close together, and the molecules are sort of crowded away from there. So here are all the different layers. We have the water or aqueous liquid molecules inside of this. We have optional the thin carbon. We have the quantifoil here, and we have the copper grid. So why would we have a thin carbon? Well, one of the advantages is that we get a little bit higher signal for the determination of the CTF, or the power spectrum. And for some molecules, for instance, like the ribosomes, it turned out paradoxically that we get more even coverage of the orientations when we use this. Gold grids, and they were introduced by Russo and Passmore at the MRC in 2014, and they were really a success. Now many people use the gold grids in preference to the copper grids, and so they discovered that the normal carbon grid sort of moves up and down, it oscillates, and using gold grids, we get a reduction by 50-fold, and there is a component that is lateral, and that of course, and here these are all different carbon uses with copper, and here is the Z oscillation for gold. So it's almost at zero. There's almost nothing there. Okay, so it's extremely stable. All these vibrations are introduced by the exposure to the electron beam by a mechanism, but that is not very well understood. Okay, now single particle approach to averaging and reconstruction. Single means unattached. Doesn't mean one molecule, but rather in the sense of the bar scene. Yeah, free from contacts with other molecules, and this affects everything in the techniques: the specimen preparation, electron microscopy, and the image processing. And again, I come back to the point: why single particles? Well, they are in the native conformation unaffected by crystal packing, because when X-ray crystallography is done, then molecules just have to assume a minimum in their conformation, in their energy, to accommodate the whole crystal packing. So we don't have any minimization here. We really observe the molecules freely in whatever they're doing. So functionally meaningful states can be visualized, and no part of the molecules needs to be chopped off for visualization, which often is the case for X-ray crystallography. And the most incredible thing now is that multiple states can be visualized from the same sample. So instead of just getting one single reconstruction out, very often we get multiple states that really reflect the function, that reflect states that are most populated in this progress of the function of the molecule. So this is ideal for looking at the dynamics of a molecular machine. The molecular machine that my group has been looking at for a very long time is the ribosome, and that has an entire work cycle that it goes through, and we very often now are able to look at multiple states in this work cycle. But a disadvantage up to 2012, there were large computational challenges. Atomic resolution was difficult to achieve for particles lacking symmetries, and we were stuck at something like 5 angstroms, and it was very difficult to go beyond this point. And then from onwards, we have still large computational challenges, but we have now the direct electron detection cameras, which have a much better performance in terms of signal-to-noise ratio and MTF. So it's a completely different world since that time, and we essentially can use the same computational procedures that were already around for a very long time, but now we get much better results, and we get very often atomic resolution. So in terms of signal processing assumptions, we have the following assumptions. All particles in the specimen have approximately the identical structure, and all are linked by three-dimensional rigid body transformations. It's rotations, translations in 3D space. So mathematically, we can simply model it in this way in order to relate one projection to the other. And particle images are interpreted as a signal part plus noise. And the additive noise assumption is an approximation, but it's been very good, a very good approximation for the purposes of the image processing. And the important requirement is that we have even angular coverage without major gaps. So this is a good coverage here, or sort of a starry sky kind of representation of all the angles that we see. This here is a bad coverage, even though it is a coverage that is akin to what you get in electron tomography. So technically, we could get an excellent reconstruction with this one here. The problem is only that the programs that we're using, they're really optimized now for this kind of coverage, complete 3D coverage. And if we use these programs to do this kind of thing, then we get direction-dependent effects, and that's bad. Okay. This is a program that is now often used in order to show the coverage by projections. You can see that in this case we have a sort of a hotspot of coverage with projections here in this area and a little bit in this area, but we never go down to all the way down to 0. Okay, I have a nice illustration of a sample on the grid. After blotting, the grid is covered with a thin layer of liquid containing the molecules. So now we have this here. This is a copper grid, and here this is the next stage where we see the individual holes. This is a single one of these, and now you see the molecules there. Okay, so these are the molecules, and you have to imagine that they're doing something. Okay, they're moving, moving around, and then comes the big chill, and now you can see that the images become pretty bad. This is a salt and pepper effect that comes from the low exposure. We need to go to low exposure because of radiation damage. So you get to an exposure that is typically in the range of maybe 20 electrons per Armstrong square. And for that exposure, we get a very large fluctuation between the average density in one point and the next point. Okay, so then we have to have some kind of a search program that finds the individual molecules, and then we put them into separate files. The previous one was a simulation, but these are actual images that have been obtained by this process. So these are ribosome images. This is an example of a micrograph of a eukaryotic ribosomes. And it's recorded with the direct electron detection camera. On film, we would never see this kind of contrast. Well, the ribosome actually has a rather large contrast because it has such a large RNA content. but even for protein molecules, we can now see very distinct views, which was never possible before when we recorded on film. So then the next steps essentially are determine the orientations of these here in some magical way, and then perform a 3D reconstruction once we know these angles. And then obviously you could see the molecules were moving, they changed the structure all the time, so the straightforward reconstruction isn't going to work very well. It is going to get a blurred image. What we ideally want to do is to perform an image classification and sort them into different bins, and then perform the 3D reconstruction. So that's indicated by here, where the subunits have different angles with respect to each other, and there could even be intermediates. Okay, I just want to note in passing that single particle methods are also used for ordered assemblies, and wherever there were Fourier methods that sort of made the process very easy for ideal arrangements of molecules, all these have been switched to single particle methods, because it always turned out that in reality we have non-ideal crystals, and the maximize the information yield from the images. It always pays out to capture very small portions and then find the actual arrangement of them. So it's been true for helical order, two-dimensional crystal order, and icosahedral order. So each time, each of these sort of different cultures of image processing sort of converged into the single particle method in the end. So I'm coming into more narrowly into some concepts that are very important to know. A signal to noise. What's the definition? Well, the signal is a predictable, deterministic part which originates from the object, and the noise is stochastic, unrelated to the signal, and aperiodic, which means that no two realizations are the same. And the signal-to-noise ratio is defined as the signal variance divided by the noise variance, and we often call it SNR. And averaging over n noisy realizations of the signal increases the signal-to-noise ratio by a factor of n. That's a rule which assumes that we have completely uncorrelated noise, and the noise is additive. And I'm giving an example for this. What is signal and what is noise in a given experiment depends on the way the experiment is designed and the way we look at it. So first of all, I just wanted to tell you about shot noise. I already mentioned that before. At the low exposure settings, which are required to avoid radiation damage, the fluctuations of the electron distribution is a prominent source of noise called shot noise. And the low exposure images typically have a signal-to-noise ratio of 0.1, which means that the signal variance is only 1/10 of the noise variance. There is extremely low signal, and compared to situations where people have been doing image processing in engineering contexts and determining the position of tanks in the landscape and so forth. So it's a completely different situation. So it also tells us that only by averaging over a sufficient number of particle projections we can retrieve the original signal. So typically we need a large number of images in order to actually realize the signal contents and recognize it. And these are simulated images of ribosome with 0.1, and that's sort of the that's what we sort of normally get. And structural noise. So this is sort of the unique situation. The matrix of ice here, or if we have thin carbon underneath, itself has a structure, and that's of course, as a genuine structure, as the structure of this here. But in the context of retrieving this structure, the structure of the underlying background is noise, because it's irreproducible from one place to the next. Okay. Okay, so averaging, we want to average over images that are like to eliminate the noise. But in order to do this, we really need to make sure that the images are, or the contents that we want to average in the images is aligned relative to each other. Because otherwise we have apples and oranges situation. So each pixel in the coordinate system has to refer to the same point of the object. Okay, so and obviously averaging in 2 dimension only makes sense for molecules presenting the exact same view, exact 3-dimensional view. So in order to do averaging of images, we need to do 2-dimensional alignment. And now averaging and alignment can be done in 2 ways. Either make use of order or symmetries to locate the individual repeats, because there is some predictability. When we see one molecule, then we know where the next one is. Or make use of cross-correlation search to locate repeats. Here, that's an active search to find actually the same object that we are focused on. And then in the first case, Fourier methods can be used instead of real space averaging. So here is an example for use of Fourier methods. This is a is a projection image of a molecule ordered on a periodic lattice. You see that the noise is completely intermixed. You don't see the structure very clearly. Now we perform a 2-dimensional Fourier transform. Now all of a sudden we see something. We see reflections where the Fourier information is concentrated in small points, and we see some kind of speckled stuff in the background, but of very low intensity. So that now the point is that only the periodic part of this structure is going to contribute to the reflections on the reciprocal lattice. And the noise part, which is aperiodic, goes all over the place, which means that the noise also contributes here, but only a very small part. And then a recipe for retrieving the periodic structure is by adopting a system of masks around each of these reflections, and then perform a back transformation, inverse transformation, which precludes all noise parts from contributing. And then you can see that we get a beautiful image of the periodically arranged molecules. Now this is what I showed here are just the amplitudes, but what we have in Fourier space is both the amplitudes and phases that are needed in order to get back here. So now make use of cross-correlation search. This is an example where cross-correlation search is used to get the images into exact same position relative to the image field, and then we can simply average them out and get such an enhanced image. And at the same time, we get a variance map and standard deviation map. So this alignment of single particles is achieved by cross-correlation. So we have translational and rotational cross-correlation. Here I'm going to show you the translational cross-correlation. So in the discrete anomalous version, you can imagine that you put one image on top of the other, and we assume that the molecule is now oriented in the same way in both of these images. And we want to know exactly how far does the molecule, has the image to be shifted from one to the next one in order to get perfect overlap between the object that is contained in them. So in order to do this, you can think about following a Duncan experiment. You have a light box, you have an image, one image which is transparency, and the other one is also transparency. Now you shift them with respect to each other in all kinds of possible positions. And for each position, you perform a cross product, which means the intensity of the light that goes through, all the way through. You make a note of this, and that is one single value. And that single value you plot into a two-dimensional matrix at the point that indicates this shift vector. Okay, so performing this entire sum or making this observation gets you one single value only. And now you proceed to do this in all possible positions, relative positions of the two images. And each time you make a note of this here. And so you gradually fill out this entire matrix with points. And then there is a particular position in which the object coincides on top of each other. And for this position, you get a very large value here. So you're going to find a peak somewhere in this whole matrix. Now, for the computer is dumb, doesn't know where the peak is, so the peak needs to be searched. The computer has to go through this line by line and find out where is a point that is larger than all the other points that has already been encountered. Okay, so it has to scan through and find this place. All right. So this is how cross correlation works. Rotational cross correlation function would be the same thing, except you don't have a translational operation here, but a rotational. So one image is rotated against the other. But in order to do that, you have to find out first find out what the translational arrangement is. So you cannot do translation and rotation at the same time. You can alternate between the two. And I have another clever method that I can tell you about, which makes use of translational invariance. Okay, Fourier transform, you might have been introduced on this already. Yeah. Okay, so here I can just skip over it. But I just wanted to remind you, if I can, that the discrete Fourier representation that I just showed you implies that the image, that we're not representing an image all by itself, but rather we represent an infinite array of these images. And that's important. It's important to understand what is happening when we use the convolution and the correlation theorem. Okay, I'm going to use the following notations. Fourier transform is, this twiggle kind of operator on this real space function. And there's always a large a capital and a small one here. The real space function is always small, and the Fourier one is large. Inverse Fourier transformation would be an f to the -1 of this function. Okay, so you can go back and forth from the Fourier representation to a real space representation, and if we use the discrete Fourier transformation, we don't experience any loss of information. We can go back and forth anytime we want. So you use, when you do program development or algorithm development, you go into the space you're comfortable in at any given time. Okay. So here we have the spatial coordinates and the reciprocal coordinates, or the spatial frequency. So one theorem that I wanted to tell you about is kind of a conservation of power, or conservation of information content. That's sort of implied in the completeness of the representation. So there's a quantity which is always the same in both spaces. So I showed you this here, and it, by definition, this absolute squared of the Fourier transform is the power spectrum. And now the total power is the same in real and Fourier space. So if we average, if we integrate over the power spectrum, then we get the same as if we integrate and perform the variance. This is exactly the same thing. Now you can see here in this case we have to subtract the average before we take the square. And here this is equivalent to taking the zero term out, the origin term, in the Fourier transform. Okay? So, in other words, you can go into Fourier space and determine exactly for any subdomain what the contribution of that subdomain is to the signal-to-noise ratio. That's important because if we have if you have the Fourier transform of an image, and we want to enhance the signal-to-noise ratio, then we could say, all right, there's only information out to a certain point in Fourier space, and anything outside is noise. So we can always enhance the signal-to-noise ratio by the factor of the areas between, the total area of the Fourier transform and this resolution domain, because we simply throw out all contributions due to noise. And this we can conveniently do by low-pass filtration. Okay, so this is the formula for computing signal-to-noise ratio in Fourier space. So we perform the integral or the summation over the signal part, and we do it for the noise part. Okay, so I want to talk about the point spread function and the contrast transfer function. Wondering, do we need a break, or do we have a break normally?
We normally have a 5-minute break.
Pardon?
5-minute break. A quick break.
Yeah, maybe that would be a good time.
Okay, now it'll be a good break.
Yeah.
See you in a couple of minutes. Have a cookie.
Cookie.
Wait, those. You break them?
You didn't see me in the morning?
I see the evening.
Personally, favorite.
But
Do what? Yeah. Right next door. They're very small. Yeah.
another. I watched definitely there's more attention. Yeah. I was watching a video.
The chance of
Yeah, I'm sure there was a lot of it. Probably.
What does it change?
Or, you know, whatever. Whatever you It happens for a couple.
Called PhD. Finishing up with this dragging process.
Okay.
Yes.
So point spread function and contrast transfer function. So in an optical instrument, not just electron microscopy, but light microscopy, the aperture limit and the aberration of the lens and other imperfections, they have all the effect that a single point in the object is imaged not as a single point, but as some kind of a spread function, and that's called the point spread function. So the point spread function can be used to characterize the instrument, and the Fourier transform of the point spread function in electron microscopy is the contrast transfer function. And in transmission EM, the CDF is given by an analytical expression. CDF is sine of gamma of k, and this gamma is the wave aberration function. There's an analytical expression which contains a number of familiar terms. The defocus, axial astigmatism, spherical aberration. Okay. Now you see how these terms go in. Here's a lambda, the wavelength, defocus, axial astigmatism, which is a defocus term that adds and subtracts depending on the azimuthal orientation. And these combined term enters with k to the square. And then the other term contains spherical aberration and goes into it with the fourth power. And CS is a spherical aberration constant. And I'm always using this notation. K is the spatial frequency vector, which is the vector in this plane, in the aperture plane, and K is simply the length of this vector. So this here is sufficient when we have the astigmatism corrected. The spherical aberration means it's an aberration of the lens that causes the outside rays to be focused closer to the nominal focus of the length. Okay, so we have a sort of a negative focus difference, and that means that wherever you go, you get some kind of a confusion, a circle of confusion. Also, the point spread function never gets to this ideal feature. It's because of the spherical aberration that lenses, the useful aperture of the lenses is tiny. It's absolutely tiny. It's in the order of 10 to the minus 2. Because we have to, when you go further in a lens, then they go closer and closer here, and you get a very big disc. So the aperture limits the rays to the useful area here, and that is the reason why electron microscopes don't have a resolution that corresponds to the wavelength. Wavelength for electrons at 300 keV is approximately 0.02 angstroms. So we never get 0.02 angstrom resolution because of this effect. So the best resolution that people get in material science, where they don't have to worry about radiation damage, is something like maybe 0.7 angstroms or something. It's in that area. We'll never get there in biology because of the radiation damage. So here's a point spread function in a 3D representation. So it has finite width, and it's centered at the location that would be expected for the single point. The point spread function, formally, the point spread function of an ideal lens would be a delta function. Delta function mathematically is a function that is infinitely high at a single point. So here's a contrast transfer function. First of all, it starts like this because we are using negative defocus. Negative defocus is used because it counteracts the effects of the spherical aberration. If you use positive defocus, then it goes in the same direction of spherical aberration. It makes the wave aberration even worse over the entire range. So we always use negative defocus. And the contrast transfer function, goes on like this here, as it is stippled in the ideal case, in which we don't have any damping effects. These damping effects are represented by envelope functions. And one effect is the energy spread, and another one is the angular spread. Energy spread, so both effects are called partial coherence as opposed to coherent. We have coherent, partial coherent, and incoherent situation. What else? Okay, so in the case of the ideal idealized CDF, which doesn't have these other effects, the envelope function is like a multiplication of this function by this kind of envelope. So this envelope that is shown is really the product of two envelopes. One due to this effect, the other one due to the other effect. Okay, energy spread means that the voltage changes, which means that the wavelength changes, or the energy of the electron changes. And defocus spread means that the defocus changes, and this has approximately the same effect as the voltage changes. So it's represented by the same envelope function. And the envelope function due to energy spread, defocus spread, is independent of defocus. And the angular spread, in this case, the point source in the cathode is replaced by an extended source. And then we get non-parallel illumination, we get convergent illumination. And which means that you can imagine that for each ray, we get a coherent situation, and in the end, we have to incoherently superpose all the different images that we obtained. And so this is reflected by an envelope function, which looks very complicated and is defocus dependent. So in the end, we have the ideal CDF times envelope function representing energy spread or defocus spread times envelope function representing angular spread. All these effects are rather small in today's microscopes because we are using field emission guns, which have very high brightness and which allows us to eliminate most of the extension of the source and really focus on one single source point. And the energy spread is also rather small because of the stabilization of the voltage. What we don't have that much control over is the defocus spread, because the particles can now be a different Z in the specimen. Okay, so we have an ice layer, and the ice layer is large compared with the particle diameter. What particles love to do is to be close to the air-water interface. So they're sitting up here or they're sitting down there. Very few particles sit in between. So if we represent the entire image field of particles by a single defocus, then we're making an error, because then we put the defocus right here. And let's say we have 1,000 angstroms here, then we have plus minus 500. So if we use this here as the defocus that we determine, then we make an error for half of the particles of 1,000 angstroms. Yeah.
So this actually depends only on the thickness of the ice.
Yeah.
But that varies. Couldn't that vary greatly within all the particles of the sample, so that the estimation wouldn't be applicable to them?
Yeah. Well, it's simply when the point is, if we represent the entire field by a single value, then we're making errors.
Okay. But
yeah. So the way to overcome this is by making defocus determinations for the single particles themselves, and some programs are doing this, but there are obviously limits to this, because if the molecule is too small, then the signal is very very poor. Yeah. You're still not.
So if you're making a CTF if you're making a correction for an entire sample, then
Correction.
the CTF
No, it's not a correction, really. It only it's not a correction, but rather this is an effect that affects your signal strength at high resolution, and the only way of getting out of it is by representing each particle by its own contrast transfer function. So if you don't do it, then the cumulative effect is represented by the envelope function, which really brings down the signal. If it brings down the signal, it means that the signal-to-noise ratio gets worse toward the higher resolution. So here are some examples for contrast transfer function. Now you always find this area where you have an extended interval. That extended interval comes from the fact that we have two wave aberrations that counteract each other when we are in the negative defocus range. One is generated by the defocus, goes with k square. The other one by spherical aberration goes with the k to the fourth. They counteract each other, and then there is an area where they counter each other, pretty nicely over, and they create a region of constant. And the first of these intervals is the so-called Scherzer focus. I think this is actually Scherzer focus, and it's named after Scherzer, who's been very involved in developing the ideas of image formation in electron microscopy. So you can see that here we have the first such area, and then here's the second one. So they're distinct defocuses in which we always get this kind of interval. Yeah, and here we have for the same settings, we have a comparison between coherent and partially coherent situation. So they are different by the effect of the angular envelope function. So the power spectrum, it's called tone rings after Fritz Tone, who was a pioneer in the use of optical diffraction analysis, or nowadays we would do a Fourier transform and look at it. Okay, why did we get these? Well, obviously the contrast transfer function goes between positive and negative intervals and has zero crossings. So this one would be negative, positive, negative, positive, and so forth. So alternating. We don't see it because we only see the amplitude of the Fourier transform. Now, why do we see this at all? And this is because we're looking at a Fourier transform of an amorphous object, and a Fourier transform of an amorphous object contains Fourier components everywhere without any gap. Okay, so that's like almost like an illumination in Fourier space, and this here sort of is a mask that is on top. You know, the instrument only allows certain frequencies in. So without this Fourier transform of the amorphous object, we wouldn't see the power spectrum. Now, of course, it doesn't need to be carbon. It can be any amorphous material. But as soon as it gets periodic, then the information is concentrated only on a few spots, and then we don't see this anymore. Okay, so what the tone rings show is how far the information is transmitted in Fourier space. So it peters out somewhere, and that's important to know. That tells us how much potential information there is to capture in the image. And then it tells you whether the lens is astigmatic, because in that case, the contrast transfer function depends on the angle in the plane. And since it's so cumbersome to figure out, you know, automatically for thousands of images how exactly these are arranged, the astigmatic images are normally simply discarded. And in fact, nowadays electron microscopes are very sophisticated, and the correction of axial astigmatism can be done in a very convenient way. Theoretically, one could make use of this information. Okay, so I already told you. Okay, so now the convolution theorem. That's a very important thing to know, and it's sort of basic to understanding everything about image formation and also about 3D reconstruction. So here's the object, and here's the image. So the situation is very easily explained if the object consists of completely separate points. In that case, each point is simply substituted by the image of a single point. Okay? So we simply place this here over there and create the image. Okay? And that operation is called convolution. It's an operation of placing the point spread function on each point of the object and then perform a sum over everything. Now, in this case, the sum is very uncomplicated because there is no overlap between the resulting image points. But it becomes more convoluted if you have an object where the values, where the points are just next to each other, because then this operation really means that for each of these points neighboring each other very closely, you have this operation, you have to keep adding up. Okay, so if I use an integral instead of the summation, so we have O is the 2D object, or the 2D projection of a 3D object, and S of R is the signal resulting from EM imaging of this object. And the H of R I call the point spread function. And then I write S of R is O of R convoluted with the point spread function, or this is the convolution product of O of R with H of R. Okay, so I introduced the symbol of this squiggle here for convolution. That stands for S of R, a double integral over the object times point spread function. Now the point spread function is shifted in all different directions. So it's an expression of what I did in the previous slide. I put the point spread function on each point of the object, and in the end, I integrate over all these products. Well, this is just a different notation, and here's it's simply a vector notation, and here's the notation in terms of the components. Okay, a special case, if the point spread function is the delta function, then this is an identity operation. Then the signal is simply equal to the object. Okay? And now the convolution theory. What does it say? It says that when we go into Fourier space and represent the signal as a Fourier transform, then that signal is equal to the Fourier transform of the object times the Fourier transform of the point spread function. So it's a simple, this very complicated expression in real space becomes a very simple expression in Fourier space. It's a simple product. Right? So in order to determine the convolution product, or in order to determine the image that we would see for a particular object given a certain instrument, all we have to do is you take the Fourier transform of the object and multiply it with the Fourier transform of the point spread function, which is the contrast transfer function. Okay? So this is object transform times contrast transfer function. That's all we need to know. So now, related to this is the correlation theorem. I showed you the expression that we have to compute in order to get the translational correlation function. This is now a very similar theorem. In fact, it's like a convolution theorem, just rearranged in some way. But in this case, we have the Fourier transform of the cross-correlation function is simply equal to the Fourier transform of one image times the Fourier transform of the other one conjugate. We take the conjugate of the other one. That's all we need to do. So instead of doing this very tedious computation that I showed you before, all we have to do is just this product. And since Fourier transforms can be taken in a very fast way in the computer, these fast Fourier algorithms, the computation of cross correlations is very fast, and we're doing these all the time. Okay. All right. So we have this one, and in this case we have a plus here. That's the only difference from before. So if we have let's say we have one image of a certain particle field, and then it's the same signal plus a certain noise term. The other one is the same, let's say, same particle but a different noise term. That would be the situation if we take two images of the same area, one after the other. Then we would have this situation, and then we want to locate exactly the same molecule in the image field. Then we would do this here, S1 correlated with that one, and so this stands for this here, and what we would get is a cross correlation of the signal underlying both plus a noise term. That noise term is simply a wash. There's nothing there, no significant contributions from that. Just want to draw your attention to this here. The special case is this is actually the special case where you have a cross correlation of an image with itself. That's called the autocorrelation function, and that has very, very interesting properties that are useful. Just as a reminder, in order to avoid the overlap that I told you about, we need to pad. We need a pad each image because the computation of the sum in real space implies that you have an overlap when you shift the images against each other. So in order to avoid the overlap, you need this padding. And here's a practical example. I'm sorry I don't have the image of the second one. So here's one of the images padded, and then there's another one here. And the cross correlation is this here. And when we draw the two coordinate axes, we see a peak, very high correlation, which is shifted exactly by the vector that brings one object in superposition with the other one. Okay, so I just wanted to show you how we can use this kind of arithmetic in order to solve a problem which seems very complicated. It's a problem using both convolution and correlation Fourier theorems. And that's the cross correlation of two EM images of an object with different contrast transfer functions. So now we have S1 and S2 of the same object signal and two different CDFs, H1 of K and H2 of K. Okay, so this is an expression of this. O of R convoluted with H of 1, and the other one is O at a different place in the image convoluted with H2. Okay, now the recipe for cross correlation is S1 correlated with S2. And now we go into Fourier space. then we find that the Fourier transform of the cross-correlation function is S1 times S2 conjugate. Or now we can replace this here with O of k times H1 of k, and the other one by O of k times H2 of k conjugate. However, since the object is shifted, we have to apply the shift in Fourier space. The shift is expressed in this way. Okay, and that gives us, now I have to simply reorder because these are simply products. It's O of k times O conjugate of k, which is now the Fourier transform of the autocorrelation function of the object. And that has now the shift term, and then H1 of k times H2 conjugate. Now this is a real space function, so the conjugate doesn't matter. It's simply now the CDFs, or a product of the two CDFs. Okay, so now back in real space, ACF, or the autocorrelation function of the object, times H1 correlated with H2, and then convoluted with delta of R, which means it's shifted. So this entire thing is shifted by this initial vector here. Now look at this. What does it mean? Now the object itself is an atomic object, which when you perform the autocorrelation function, you get a huge contribution exactly where it's exactly at zero. So it is almost like a delta function on this scale. So it's a delta function convoluted with the cross-correlation function of the two point spread functions. And sort of depending on whether the point spread function is very close to the other one, or we might get a pretty nice cross-correlation between the two. If they're very dissimilar, because the defocus is very different, then it might be a very extended blurry function. And that is shifted by the vector that we were looking for. So this is sort of neat. What it tells us is we can sort of disregard here this one, and we can just focus on the relationship between the two point spread functions. It tells us that if we want to look for an object in a noisy environment, then and we know the CTF, we should really apply the same CTF to our reference, because then we optimize this here, and we get a very nice and sharp peak. So this is sort of an example how we can very quickly derive a solution to a rather complicated problem. It looks very complicated, and if you had only the instruments of real space in real space, then you would be sort of lost. And these theorems make it very easy to look through this. This is what we get if we if we look at the cross correlation of the point spread functions as a function of the difference in defocus. You can see that depending on the focus difference, we might get we might even get a zero in the peak, or we might get negative peaks. So this is such a display of different defocus differences and what it means for the cross-correlation peak. Here you can see a very extended peak. Here you see a very sharp peak in the center. Okay, so but the cross-correlation itself is affected by noise. So you can have very noisy situation, and then it might become difficult to recognize the peak standing out from the variations of the background. So this is this was an equation which we formulated very early on to find out how big does the particle need to be in order to get significant cross-correlation in a situation where we have to minimize the dose. So we have to minimize the dose in a certain way, and then we're aiming for a certain resolution, and we have a certain contrast. That means that the particle has to have a minimum size in order to make the cross-correlation peak detectable. And that was the formula that we wound up with. So here's the particle diameter, the contrast, the resolution we're aiming for, and the critical dose. So, later on, there was a very, very detailed analysis of these relationships by Richard Henderson, and I recommend you to look at this article. Richard estimated the number of molecules of a given size required to reach 3 angstrom resolution based on the scattering data, and he did it for electrons, X-ray, and neutrons. So it's a very comprehensive paper, and it's a very good source of information. Okay, so I told you before that we have the problem that when we do translation alignment, and we need to have the molecules already correctly oriented. If we want to orient them, then they already need to be translationally aligned. So how do we ever get started? So the thing to do is iteratively, and there is one problem, which is the reference. We get different results depending on which reference we use. And sort of to cut through this, you can start with a reference, and then you don't go on with the same reference, but rather you form the average of this first of the results of the first pass, and so that gives you a new reference. And as you go on, you get more and more reference independent, or independent of the choice of the first reference. So the other one is that's the multi-step alignment that I told you about. So now there's a way of doing this by using of invariants, such as the autocorrelation function. So the autocorrelation function is translation invariant, but it retains orientational features. Okay, so here's is there something else missing here? Okay. All right. So we have an image consisting of 3 dots right here. The autocorrelation function looks like this here, because when we shift the image on itself, we don't see anything until this dot coincides with that one. So we get this signal here. And we get the same signal on the other side because we can shift it in this way, right? And the same as this here. This gives us these two spots. And these here give us these two. Wait a moment. Yeah, this one and that one. Okay, so the autocorrelation function of these system of 3 dots has 7 maximum, and the 7th one is the one in the origin where all dots are superposed on each other. So it has a very, very strong weight. Has the highest weight of all. What it tells you is the autocorrelation function is centrosymmetric, so you know where the origin is, and it has certain features of the object. These directional features are retained here. Okay? So if you have 2 of these images in arbitrary translational positions, they always produce the same autocorrelation function. So if you have 2 identical ones, and they appear in different places in the image, you always wind up with this one here. So this gives us a recipe to use the autocorrelation function in order to do the rotational alignment. Because we can always do this no matter where the image is in real space. Okay, this here an example. Here's a molecule, here's the autocorrelation function. Here we have the molecule in arbitrary positions, and here are the autocorrelation functions of these. Always centered, and you see the same function essentially in different orientations. So that essentially is expressed in this theme. There's an autocorrelation function based alignment method. So you have you have 2 images here and here, and in each case we have to do the padding that I told you about that is necessary. Then you compute the autocorrelation function, and now these functions are rotated by a certain amount with respect to each other. Now you do an angular cross correlation that gives you a certain peak at a certain angle, theta. You feed this theta to the second image, make a rotational adjustment of this image, and then you're sure that you have the images in the correct orientation. Then you go on with the cross correlation. And there's only one thing wrong with this, which is that 2 images that are rotated by 180 degrees have the same autocorrelation function. So in this scheme, we have to interrogate. We have to do it twice. We have to probe the 2 different orientations and find out which one gives us the highest signal. Right? But the entire thing is now a workflow that always gives us the correct translational and rotational alignment. So, how long are we going to?
We're actually over time.
If we're already over time.
So, a couple minutes to wrap up. It's very hard.
Yeah, sure. But I simply stop. You know. So, yeah, so I just want to show a few slides. And so the variance map is a byproduct of the averaging, and can be used to find regions where the images on average differ maximally, and it's a yardstick to show us whether or not a density at a particular point is significant. So this is the thing that we always get as a byproduct of the averaging, and here it is shown in such a variance map of this very old application of the averaging. And the very interesting thing here is that the variance is concentrated around the border. And this is because this is a situation of negative stain, where the image is really the image of the molecule that is created by stain exclusion. And the main component of variance has something to do with the fact that the stain laps up to different extents. And it's a meniscus effect. So the highest inconsistency is really exactly on the border, because the stain is different heights close to the molecule. So I can stop here.
Yeah.
I think.
Well, you can see Joachim's passion for image analysis, but he won't promote his own book, but I will. So there's a very useful textbook. We don't have many textbooks in the EM field. It's called 3-Dimensional Electron Microscopy of Macromolecular Assemblies. I think we have like 3 or 4 different copies around the lab if you would like to borrow one. So then the slides will go up online, but then next week we'll continue with Amadeda George and Reza Kayat on the second part of single particle. So we'll see you soon. If you have any questions, though, you can email emg@nysbc.org or Joachim directly.
Yeah. Okay.
Okay, thank you so much.
Thanks. I have to see where I am here in the slides. I'm at 76 of 114.
Oh my goodness. It's really hard to condense the
Yeah.
whole. Do we
Well,
have a copy of your presentation?
It's on
here, so that's
yeah,
fine.
because we copied everything.
Do you
over.
want to include everything, or is there anything we should edit, or can we just?
No,
we'll
you
just-
can throw everything in.
We'll put it
there.
as a whole PDF
Yeah.
and we'll put it online. Okay, thanks so much.
You guys reflect to that.
The typing is way better, but
There's a lot of overlap.
Yeah, which is nice. It's I think it's kind of an iterative learning process.